It's my mic on.
Yes, you're right. I can hear it.
So why is surface area of the sphere is a derivative of volume of the sphere? So what we know from high school, the volume formula of the sphere is 4 over 3 pi r cubed. And doing simple derivation, it dv over dr gives us 4 pi squared, which is the surface area formula of the sphere. So there are two proofs. Proof one, proving that volume of the sphere of this shape is the integration of the surface area. The first step to establish an integration in multiple dimensions to establish volume of an object in nth integral. So volume equal eth integrals of 1 dx1 to dxm, where e represents the mth integral and m represents the dimensions. So e equal ball radius r in rm or all real r in m dimensions. So first of all, we do a change of variables where u1 equal x1 over r, u2 x2 over r, etc. to um xm over r. We then apply those u1 to um to the ball radius r to ball radius 1. So since e is the ball radius r in rm, so this is because of essentially its size divided by r, the radius becomes r over r, which essentially equals to 1. We then need to calculate the Jacobian to give the determinant of all possible derivatives. We can set up by du1, du2, or it's dum equal the Jacobian of du1, dum over dx1 to dxm to dx1 or dxm. Expanding the Jacobian gives us partial u1 over partial x1, and all the way to the right gives partial u1 over partial xm. And down from the top left is partial um over partial x1, and all bottom right gives us partial um over partial xm. Solving the partials and give us 1 over r, gives us 1 over r diagonal matrix. Then the determinant of a diagonal matrix is the product of the diagonals, which is 1 over r times by itself m times. We then can say that du1, du2 to dum equal to 1 over r squared, r to the power of m, dx1, dxm. Which then, if we put the rm to the opposite side, we can convert to x1, dx1 to dxm equal to r to the power of m du1, dum. So after the change of variable, then it can change the integral formula. So the r to the power of m can come up to the front, and the mth integral of 1 over e gives us r to the power of m over integral of e dash 1 du1 dum. And then since the integral of 1 over e dash simply the volume of e dash, then we can, since volume of e is a constant, we can call it c, which then gives us the volume formula v equals c rm. So to further expand this equation, so in two dimension is a constant times r squared. And certainly the area of the disk is pi r squared, where pi is the constant and r to the second dimension m equal to 2. And in three dimension, it's constant time r cubed. And in fact, the volume of the sphere is 4 over 3 pi r cubed, where over 4 over 3 pi is the constant, and r to the power 3 is in the m in the third dimension. And this proves that it can hold on to higher dimensions where m can be 4, 5, 6, and the constants can varies. So the second proof is find volume by integrating the area using the divergence theorem. So we set the similar volume formula by integration like the previous proof. And finding some vector field f proportional to the point s on the sphere so that divergence equal to 1, where f equal to x1, xm equal 1 over m vector x1 to xm, which then x1 over vector x1 over m to xm over m. And using the divergence of f is x1 over m x1, etc. all the way to xm over m xm, which gives us on 1 over m plus itself by m times. And the volume of the m integral of 1 using divergence f also concluded in 1. So this is a Gauss-Green theorem. The theorem relates to the integral of the divergence in the flux over the surface area of E. So the volume formula then converts into integral of E, divergence F, dx1, dxm. And the divergence theorem then converts into double integration of SF des, where S partial E is sphere radius R in Rm, which then turn to integration, double integration S F times n, where n is a unit normal vector of S. So at every point of S in the sphere, there's a normal unit vector, and taking vector fields F at every point dot with normal unit vector. And so why is this useful? Because for the sphere, the normal unit vector is very easy to calculate. So this further expansion on the unit vector, n hat is equal to x1 to xm vector. And for the unit sphere, you just take the normal vector and divide by length, since since for any vector get unit vector, just divide vector by the length. So n equal n hat over distance for n hat. And n hat is x1 to xm, and distance n hat squared x1 squared plus xm squared. And it's since because like we're exactly on the sphere, so and not on the wall, so quantity for the distance of n hat is actually the r or radius. We can then substitute it into the earlier integral formulation of divergence theorem. We give us double integration sf dot n ds, then f, since f is already x1 over m there, we can convert it to f equal x1 to xm over m, and n is x1 to xm over r, like above. And we can then put 1 over mr to the front, which gives us the dot product of two vectors x1 and its dot product of itself, which turns into x1 squared all the way to xm squared ds, which is r squared if we look at the n formula. And we can also put the r squared to the front over mr, double integration of s1 ds, where double integration gives us the area. So it concludes to r over m, volume equal to r over m times the area. So using the last two proof, proof 1 gives us volume equal r to power of m times the constant, and proof 2 is volume equal r over m times the area using the divergence theorem. Now we can equate these two formula, v equal v. So r to the power of m times constants equal to r over m times area. And if we can shift m over n over r, the area formula gives us c m r m minus 1. And since volume is equal to r to the power of m times c, so we can derive this formula with derivation of v respect to r, which then give us m comes to the front, and m minus 1 gives us m times r minus 1 times the constant, which is the area formula. So this proves that the derivation of volume is the surface area. And since this proves are non-numeric in m dimension term, it can hold on to high dimensions. Thank you so much for listening. Yep.
Okay, so you guys have, yeah, that's what I was waiting for. All right, thanks very much, everyone. That was really